Thank you. So first of all, thank you everyone for being here, and thanks to the organizers for giving me the opportunity to speak. So today I'm going to talk about large genus asymptotics of intersection numbers. So this is a joint work with Elba and Paolo that are both here, and with Bertrand Hénard and Danilo Levansky. So as I said, I don't have to motivate a lot the study of large genus asymptotics in front of this audience, but nonetheless, let me start with an easy example that you probably are all familiar with. So let's suppose I give you an enumerative problem which goes like this. So suppose you want to count the number of arrangements of m distinct objects into m distinct boxes. So this is a very easy enumerative problem, and the solution is just the factorial. And the reason why you get the factorial is because, well, if you have m distinct objects, let's say you want to try and put an object into the first box. So you have m possibilities to choose from, and once you put this object inside the box, then you are left with m-1 objects that you have to put into m-1 boxes. So in this way you get this recursive formula that gives you the factorial. And the nice thing about this formula is that it's exact. It solves the enumerative problem you started with, but the disadvantage is that this formula is recursive. So it doesn't tell you exactly how this number behaves, right? And so one solution to this is to look at the asymptotics. And for this specific problem, this is solved by Stirling's approximation formula, which is given here. And so the disadvantage of this formula is that it's not exact, it's just asymptotically exact. But the advantage is that it's a closed form expression. So with this formula, you can actually understand how these numbers, this enumerative problem, the solution to these enumerative problems behaves. And if you want to be more precise, what you can try to do is to try and improve on this error here by looking at subleading corrections to this formula. So if you do this for this specific problem, what you can find at first order is this 1/12 times m to the -1, and the error now it goes like m to the -2. And you can go on. For example, if you go to the second subleading term, you get this 1/288 m to the -2. And so in general, you can try to visualize this asymptotic formula in the following way. So if you take m factorial and you divide by the leading asymptotic and you subtract -1, what Stirling approximation formula tells you is that you're just you're left with an error that goes like m to the -1. And so if you plot the left-hand side of this equation, you get some dots here. And as you can see, they approach rapidly 0 like m to the -1. And if you look at the subleading correction, so you add this 1/12 m to the -1. So this is the green dots here. You can see that this approaches 0 way faster. In this case, like m to the -2. You can try to plot here the third correction. You don't even see the improvement because it's you should zoom in to understand that you're doing even better. So this is a problem you're probably familiar with, but the main point here is that you started with an enumerative problem. You managed to solve it with a recursive formula, but the recursive formula is not the end of the story. And you can try to understand the asymptotics, maybe with all subleading corrections, to get a better grasp on how these numbers behave. And the enumerative problem I will consider today, this already showed up in Eli's talk this morning, is that of the computation of some, the so-called psi-class intersection numbers. So if you don't know anything about intersection numbers, that this is fine. The main point here is that I will consider this collection of numbers that I will denote with this tau d1, tau dn. So these are given by some integrals over the moduli space of curves, and they depend on a tuple of integers, d1 up to dn, that sum up to 3g minus 3 plus n. So secretly, this tuple here, it depends on a genus parameter, which is given by this equation here. As Elise explained, these numbers, they pop up in an enumerative problem, which is the enumeration of metric ribbon graphs. So this is the, if you want, the enumerative problem that it's lurking around here. And well, apart from this specific enumerative problem, these intersection numbers are kind of important because they actually show up in many applications in enumerative geometry of surfaces. So for example, they show up in the computation of Weil-Peterson volumes, so hyperbolic geometry. As we saw in Eli's talk, they show up when you try to do flat geometry, so Mesurvich volumes, multi-curves counting, and so on. They also show up when you try to compute Hurwitz numbers, Gromov-Witten invariants, and so on. So, and from the physics point of view, they also appear when you try to compute the partition function of topological 2D gravity. So there are also some physics connection here. So this is the enumerative problem, and the question is, how do you compute these numbers? And the answer was first conjectured by Witten and proved by Kontsevich in the early 90s. And the solution goes like this. So first of all, let me introduce this normalization. I just take these intersection numbers and I normalize it by this double factorial. And the solution proposed by Witten and proved by Kontsevich is this recursion here. So please don't try to understand the details of this recursion. The main point here is that this formula here is a recursive formula. So if you try to draw what's the moduli space that it's behind all these intersection numbers, you will see that the left-hand side is something related to genus G curves, surfaces with n boundaries, let's say. While on the right-hand side, you have the terms that you get when you try to cut out of a pair of pens from this surface. And because of that, this kind of formula, it's called a topological recursion, because it's a recursion on the topology of this kind of surface. So if you want to keep in mind the analogy with n factorial, this equation here, it's a recursive solution to the problem. So now we're very happy because we can plug this into a computer, and from these initial data, you can compute these intersection numbers. But the problem is that this recursion doesn't tell you how these numbers behave. So, and this actually showed up again in Eli's talk. One would like to understand what's the large genus asymptotics of these intersection numbers. And the statement here is that the large genus asymptotics of these intersection numbers is given by a formula like this. So you have an overall constant in G, which is 2 to the n divided by 4 pi. And then you have a factorial behavior, a 2G factorial behavior, which is given by this gamma function of 2G minus 2 plus n, divided by an exponential behavior, which is this 2 over 3 to the 2G minus 2 plus n. And this formula was conjectured by Vincent, Elise, and Anton, together with Peter Zograf in 2019. And it was later proved by Agarwal and reproved by Guon Yang. So this formula is known, but somehow what I would like to explain today, it's how to understand a bit more this formula with a new proof that I'm going to propose. And so the questions that I want to address today is, well, first of all, is there a new strategy to compute this kind of asymptotics that it's in some sense more universal? So what I mean by this is that if you look at the proof of Agarwal and the one of Guo Yang, the proof is extremely nice, but the downside is that their proof is kind of ad hoc for this problem. And the structure of this problem is not so isolated. There are many problems in enumerative geometry that have exactly the same structure. So what I would like to address is, well, is there a more universal strategy to try to compute this kind of large genus asymptotics formula? And another question I want to address is what is the geometric meaning of this formula? So for example, here you can see this 2/3 appearing here. Why do we have 2/3? What's the meaning of this, this number here? And the last point, like in the Stirling approximation formula, is what about the subleading corrections? Is there a way to go beyond this g to the -1? And the answers that I want to give in today's talk is, well, first of all, we are going to propose a strategy that it's somehow suitable for different enumerative problems. And this strategy will involve resurgence and the determinantal formula. So I will try to explain in the next slides what these two ingredients are. With this strategy, we will also show why this, for example, this number 2/3 will pop up. And this, in the specific case of these Witten-Kontsevich intersection numbers, this is due to the presence of an underlying differential equation, which is the Airy differential equation. And with this strategy, I will also show you how to compute all subleading corrections to the formula. And so the final answer will look something like this. So the large genus asymptotics of the intersection numbers is given by this formula here, which is an improvement of Agarwal's formula in the sense that we have these subleading corrections. And here I left these values S and A like this, but the main point here is that we also get an explanation for these values, S, A, and all these alphas. And more specifically, this S here is equal to 1. And it's given by the Stokes constant underlying the Stokes phenomenon of this differential equation. I will explain what I mean in the next slides. This constant A, which is this 2/3 that I was talking about, is the constant appearing in the exponential behavior of the Airy function. So there's also an explanation for a geometric, in some sense, explanation for this A that also appears here in all subleading corrections. And finally, we get an algorithm to compute these constants appearing in the subleading corrections to this series here. And we also managed to prove some properties satisfied by these constants. For example, these alpha k's are polynomials in N, and they're also polynomials in the multiplicities of these indices di that appear in the intersection numbers. So just to give you an example, the first constant, alpha 1, is given by this complicated expression, which is simply a polynomial in N. And it's a polynomial in P0, where P0 is the number of di's that are equal to 0. Okay, so this is somehow a new phenomenon that appears in the subleading corrections that was not present in the leading one. Okay, so the rest of the talk would just be an explanation of this formula and how we got this result. But before going into this, let me say a bit more about these subleading corrections. And I can show you with some numerical data how to see this dependence on the di's that you can see in this alpha 1, for example. So if you arrange the formula that I just showed you, you can actually isolate this alpha 1 in this way. So if you rearrange the formula like this, you can compute alpha 1 up to corrections in 1/g. And as I was saying, this alpha 1, it depends on the di's. And one can see this by plotting the left-hand side of this equation for different values of the di's. So here I'm taking n equal to 2. And these dots are different choices of the tuple d1, d2, which you should remember, they have to sum up to the dimension of the moduli space. But as I said, this alpha 1, it depends on P0, which is the number of di's that are equal to 0. So if you plot the left-hand side here, you should see a different behavior when you have at least one di which is equal to 0, which is the case of this blue sequence. And you should have the same convergence when you don't have this. And this clearly comes up in the numerics. Okay, so the rest of the talk now, it's about how we got these results. So as I was saying, there are two main ingredients. One is resurgence, and the other is this determinantal formula. So let me start with the resurgence first. So here I said resurgence, but actually we don't need sophisticated tools from resurgence. We actually need some all the results that are due to Darboux and Borel. So let me start with the idea of Darboux. And this insight of Darboux goes like this. So imagine you start with a convergent series. So this phi hat, which is a convergent series. And imagine you want to understand what's the large n asymptotics of the coefficients of this series. Since this series is convergent, you get a holomorphic function at the origin, which you can analytically continue. And the idea of Darboux is that if you want to compute the large m asymptotics of these coefficients, this is totally controlled by the behavior of the analytic continuation of this function at the singularities. So I will give more details in the next slide, but let me first explain what's the idea of Borel. So the idea of Borel, it goes like this. So imagine now you start with a divergent series. Let's imagine you have a divergent series where the coefficients am, they grow like m factorial. So if you suppose you have a behavior like this, you will get a divergent series. And the idea of Borel is, well, to take this divergent series and force it to be convergent. And you can achieve this by taking the same series but dividing all coefficients by their factorial growth. And if you do this, this is called the Borel transform. Now you get a convergent series, and now that you have a convergent series, you can go back to Darboux and apply the same method to get the large order asymptotics of the coefficients of your original divergent series. Okay, so these are the two main ideas that I want to convey here. Let me be a bit more explicit about this insight of Darboux. So let me briefly sketch the proof of this. So imagine, again, you start with a convergent series. And suppose that when you take the analytic continuation of this convergent series, you have only one singularity that it's of log type, of logarithmic type, located at s equal to a. So what I mean by having a logarithmic singularity is that you can express this function phi hat as a logarithm at s minus a times a holomorphic function at a plus possibly another holomorphic function at a as well. So this equation here is what I mean by having a logarithmic singularity at a. And so in this setting, I don't care too much about this additive holomorphic function. What I do care about is the holomorphic function multiplying the logarithm. So let me give a name to this holomorphic function. Here, it's a bit out of the blue, but it will maybe be a bit more clear in the next slides why I chose this normalization. So I want to call the holomorphic, I want to normalize the holomorphic function multiplying the log in this way. So here, again, A is the location of the singularity. This S here is just a constant. I will call it the Stokes constant. And this phi hat evaluated at S minus A, it's called a minor. And because this has to be a holomorphic function at A, psi hat has to be a holomorphic function at the origin. And because it's holomorphic at the origin, I can Taylor expand it and get some coefficients that I call BK. Okay, so this is the setup. Okay, so what can I do with this? Well, first of all, you can extract the mth coefficient from your original series using Cauchy's formula. So you just take a small contour around the origin, and by performing this integral, you get the mth coefficient. But now you know more about this phi hat. You know that it has a logarithmic singularity at A. So if you start enlarging this circle, you will end up with something like this, where you have to avoid the log singularity with the logarithmic cut. And well, under some other assumptions that I will hide under the carpet here, you can actually extend this contour to infinity, and you will end up with a Henkel contour that is getting around the logarithmic cut. So you end up with an expression for the nth coefficient that looks like this. But now what you can do is take this expression here and insert it in this formula. So when you do this, this holomorphic term will not play any role because you're integrating it along the Henkel contour. So the only interesting part is given by this logarithmic part. And the main point here is that the log has a discontinuity along the cut, which is 2 pi I. So if you use this, you will end up with a single line contour along the cut of this minor here with the Stokes constant in front. And the last idea here is to take the Taylor expansion at the singularity here, insert it inside this integral, and with some other assumptions, you can massage this a bit, and you get this asymptotics here. And so the main point that I want to convey here is that using this idea, you can get the full asymptotics of these coefficients, with also the subleading terms. And the only quantities that appear here are the Stokes constant, the location of the singularity, and the Taylor expansion, the expansion coefficients of this minor here. So in this specific situation, as long as you are able to compute S, A, and as many coefficients of psi hat as you want, you can get this asymptotic formula. It's completely true. In principle, you can. In many examples, S and psi hat will have like a natural interpretation, so I want to keep them separate. But in this example, yeah, in principle, I can absorb S and 2 pi inside psi hat. It's just convenience for later. Okay. So if there's something that I want you to bring home from today's talk is the following slide. So. Imagine you start with a divergent series and you want to understand the large M behavior of the coefficients. The strategy is to take the Borel transform, make it convergent, studying the location of the singularities, the Stokes constants, and the minors at the singularities. And as soon as you can compute all of these quantities here, you get the large M asymptotics of the coefficients. Okay. So this is the formula that I explained, but in the case where you have more singularities. Okay. So let me give you one more example before going to intersection numbers, which is the example of the Airy differential equation. So if you take this differential equation here, what you can try to do is to compute the formal WKB solutions of these equations. And if you try to do this, you will end up with two solutions called the formal Airy and Berry functions. The Berry function is just the Airy function evaluated at minus h bar. This is because this equation has a symmetry when you plug minus h bar. And the main point here is that this psi hat has an exponential behavior times a formal power series in h bar. So I don't like this exponential behavior here, so let me separate it, and I will denote with psi tilde essentially everything but the exponential behavior. So now this psi tilde is a formal power series, and it's not hard to see that this is a divergent series. So you can try to apply what I just explained. So you can take the Borel transform and try to study the location of the singularities, the Stokes constant, the minor, and so on. And this is not so hard. And if you do this, you can see that there is one log singularities located at 4/3 x to the 3/2. And the Stokes constant in this case is just 1. It has a geometric meaning. This is why I keep it separate. I don't have time to explain it, but it's very nice to see why you have this 1 here. But most importantly, the minor, this holomorphic function that appears in front of the log, it's the Berry function, which is quite surprising because you were starting with the airy function. Now you're looking at its analytic continuation. And in principle, there's no reason why you should get the Berry function at the singularity. But this is the case, and this is the case in a much more general setting involving this kind of Schrödinger type equations. And this also explains a bit the name resurgence. You are looking at the airy function, and at the singularities of the airy function, you see the Berry function appear. And so the upshot here is that for the airy function and the Berry function as well, we know everything. We know the location of the singularity, which is 4/3 x to the 3/2. We know the Stokes constant, which is 1. And we know the minor, which is the Berry function. OK. So I just explained to you how, like a strategy to get asymptotics of some divergent series. So let's try to apply now this strategy to the case of intersection numbers. So the first thing to do is to try and put them in a generating series. So what I want to do is to put all these numbers in a generating series like this. I want to keep track of the genus with this h bar parameter. And these WGN here are just a generating series of intersection numbers with that genus G and that number of insertions N. So the main point here to keep in mind is that I have a fixed N. H bar is keeping track of the genus, and these variables xi, they keep track of the indices of these psi classes. OK, now we have a generating series. It's not too hard to see that this is actually a divergent series in H bar. So the idea is, well, can we take its Borel transform and study its singularities? And if we can do this, then we can apply the machinery that I just explained to get the large genus asymptotics of the intersection numbers with the subleading corrections, because this strategy also gives you the subleading corrections. And so, of course, so this is the main strategy, but the problem is, how do I achieve this point 2? How do I compute the location of the singularities, the Stokes constants, and the minors? So this is the main problem, and this is where this determinantal formula comes into rescue. So this determinantal formula, it's something that is different from this Witten-Kontsevich recursion that I explained at the beginning. It goes like this. So let me first introduce some notation. First of all, I take the airy functions, these formal airy functions, and let me arrange them in a matrix like this, where I have the airy function, the Berry function, and its derivatives. And because of the choice of normalization of those functions, this matrix here will be an element of SL2C. It has determinant 1 because of that specific choice of normalization that I took. This function here now satisfies a linear ODE. All good. So the next thing might be a bit mysterious, but there's a nice explanation for this. So what you can do now is you can define another matrix that I call M, which is just the conjugation of this constant matrix, which is the Cartan generator of the generator of the Cartan algebra of SL2, and you conjugate it by this psi. So what you get is this explicit matrix here, where the most important part here is that in M it's a matrix where every element, it's a quadratic product of airy and Berry functions. And what it's important here is that it's always airy together with Berry. You never have things like airy squared or Berry squared. It's always airy coupled with Berry. And because of this, if you remember these Airy and Berry functions, they have an exponential term in front. But because I have Airy times Berry and they differ by a change of sign in H bar, the exponential terms, they cancel out. So if you remember, I used this tilde when I got rid of the exponential. And since they all cancel out, I can replace all this psi with their tilde version. And so now M is actually a formal power series in H bar. Good. And so the last ingredient to state this determinantal formula, it's the notion of cyclic permutations. So a cyclic permutation of order n is just a permutation sigma that has no fixed points. And you can visualize this a cyclic permutation like this. So imagine you take 1, a cyclic permutation will send it to sigma 1 and so on. So that at the end you will get a single cycle of length n. And the statement of this determinantal formula, which is due to Berger-Renard from the topological recursion point of view and by Bertola, Dubrovin-Young from the KDV point of view, is that the generating series of these intersection numbers is given by, well, a sign that it's not so important, times a sum over all cyclic permutations of n elements, where n is the number of mark points. And for every permutation, you have a ratio of two quantities. At the numerator, you have a trace of a product of these m matrices that I defined in the previous slide. And you have n of them, and they differ by the value of this x variable. So in order, you have x1, x of sigma 1, and so on. So you essentially change the value of x following the cyclic order of the cyclic permutation. And at the denominator, you have this difference, this product of differences of x1 minus x of sigma 1, and so on. Okay, so this is the statement of this determinantal formula. So a quick example is n equal to 2. In this case, there's just a single cyclic permutation of two objects, which is 1 goes to 2 and 2 goes to 1. So you have only one term in this sum, and you get this formula for W2. And if you insert the expression of M and compute this trace, you get a kind of complicated expression in the Airy function, the Berry function, and its derivatives. But the nice thing about this expression is that once you plug in this formal power series that I gave in a previous slide, and you expand in H bar, by looking at the different coefficients of H bar, you get the 2-point intersection numbers. Okay. And why is this formula relevant for me? Well, the main point here is that this formula, it's a kind of closed formula for the generating series of intersection numbers. And this closed formula involves only Airy and Berry functions that I perfectly understand in terms of singularity structure of their Borel transform. So the main point here is that since I know the singularity structure of the Airy and the Berry function, I can somehow push this knowledge to a knowledge for the singularity structure of the Borel transform of this n-point function, this Wn. So this is maybe a bit tricky to see here, but the main point is that all this resurgence business is well behaved when I consider products and sums. And as you can see from this example, this W2, for instance, is just a product and sums of Airy and Berry functions, which I perfectly understand. And I can push the knowledge of these building blocks to a knowledge for this object here that I want to understand. And so by putting all the pieces of the puzzle together, what we can find is that this, the Borel transform of the generating series of these n-point intersection numbers has 2n logarithmic singularities. And these 2n logarithmic singularities are located at these two different values here. It's 4/3 xi to the 3 half and the same with a minus sign, where I goes from 1 to n. And the first singularity is given by essentially the appearance of the Airy functions with variable xi, and the second one is given by the presence of the Berry function with variable xi as well. And again, since I know everything about the Airy function, one can also compute what's the Stokes constant. Yes?
So is it hidden in the discussion that this generative function is the solution of a certain differential equation? Previously you understood the operator?
Yes, so one can show indeed that W, so from the fact that the Airy function is a solution of an ODE, you can push this knowledge to get a differential equation for Wn. It's a consequence of the fact that you know. No. I mean they're both independent in some sense. You don't need the fact that Wn is a solution of an ODE. It's true, but just and in principle you don't even need that the Airy function is a solution of a differential equation. You only need to know the singularity structure of its Borel transform. A way to compute that is using the Airy ODE, but in principle you don't need that. So as I was saying, from studying the Airy and Berry function, you get the location of the singularities. And you can also compute the Stokes constant at each of these singularities is always 1. And you can also compute the minors, which is maybe the most tricky part. Here, I don't want to give too many details. If you want, we can discuss this later, but the point is the following. So if you try to compute the minor associated to the singularity located at plus 4/3 xi to the 3/2, what you can do is take the determinantal formula, and every time you see the Airy function with the evaluated at the ith variable, you substitute it with the Berry function, and vice versa. If you have if you want to look at the minor at the singularity minus 4/3 xi to the 3/2, every time you see the Berry function evaluated at the ith variable, you substitute it with the Airy function with the same variable. And if you recall the theorem that I explained at the beginning, as soon as you have all these quantities, you immediately get the large genus asymptotics for the generating function. So by putting all these ingredients together, what we got is this formula here, which at leading order gives you the result of Agarwal. But by looking at the expansion coefficients of these other minors, we also got the subleading corrections. And not only this, but because of the strategy, we also understood what's the geometric meaning behind all these quantities. So as I was saying at the beginning, this overall constant S is equal to 1, and this is just the Stokes constant of the Airy differential equation. This value here that appears in this exponential behavior, it's 2/3. And this is a consequence of the fact that the Airy function grows exponentially at rate 2/3. And from this computation, we also got an algorithm to compute all these subleading corrections. And by the knowledge of these minors, we also managed to prove some properties satisfied by these alpha k's, like polynomiality in n and the multiplicities, which was originally conjectured by Guo Yang. And again, these alpha k's, they are explicitly computable, and the coefficients of n and these multiplicities are just some expressions in terms of the coefficients of the asymptotic expansion of the Airy functions. Okay, so this is what we got for this psi-class intersection numbers problem. But as I was saying at the beginning, the main point about this method is that it's not it's not valid only for this kind of problem. It's more like a universal strategy to attack problems that have the same structure. So what I want to do next is just conclude with two more examples that we studied. So the first example, it's again intersection numbers that are slightly different from the ones that I consider. These are called Norbury's intersection numbers, and they appear when you try to compute, for example, super Weil-Peterson volumes, or in the context of this BGW tau function of the KDV hierarchy. And these intersection numbers, they have more or less the same structure. You have to intersect psi classes, but with a new cohomology class, which is this theta gn. And again, when we normalize these intersection numbers with these double factorials, we get exactly the same type of asymptotics. So the formula here is exactly the same as the one before because the problem has exactly the same structure. The only thing that changes in this case is the differential equation that it's underlying this problem. And in this case, the differential equation is the Bessel differential equation. And so in this specific case, what you can see from the Bessel ODE is that the Stokes constant is not 1 anymore, it's 2. So now this value here, it's going to be 2. The exponential behavior of the Bessel function, that it's a solution of this ODE here, it's 2. So this constant A here, it's now 2. And with exactly the same type of strategy, we also got some formulas for the subleading corrections with the same type of properties. They are polynomials in n and the multiplicities, and they are computable in terms of the asymptotic expansion of the coefficients of the Bessel function. And let me conclude with one last problem, which is in some sense way more complicated, but the same strategy applies. So these are called R-spin intersection numbers. And again, the structure is very similar. You have these intersection numbers that are intersections of psi classes with now a class that depends on some parameters. This is called the Witten R-spin class. And I want to normalize this with this R factorials. And when you apply exactly the same strategy to these numbers, you get something much more complicated because essentially the ODE that it's underlying this problem, it's a higher order. But nonetheless, the same strategy applies. So we get an explicit large genus asymptotics for these numbers that now has more contributions because the ODE is higher order. And the ODE in question here is called the R area ODE, which is of order R, so this is why you get many more contributions. But the point here is that the strategy applies nonetheless. And yeah, I think we all want to go to lunch, so let me stop here. Thank you.